So today's meeting is on number theory, and we'll be talking about some applications, including like cryptography, but also just like some basic introduction to number theory for those who aren't familiar with it yet. So yeah, we'll start off with an intro to some of the relevant number theory for today's lesson. So the first thing we're going to jump into is a review on the modulo operator. So the modulo operation returns the remainder when one integer is divided by another integer. So keyword here is the remainder. So for example, 21 modulo 4 is 1 because 21 divided by 4 is 5 with a remainder of 1. So in other words, this is 21 is equal to 4 times 5 plus 1. And then this remainder, this result, is also known as the residue. So another way you could say it is 1 is the residue of 21 modulo 4. And then mathematically, this is written as A is congruent to B modulo n for some integers A and B. And then you can notice the fancy congruence triple equal sign. And then this sign is called the congruent sign. And mathematicians prefer that you use the congruent sign instead of the regular equal sign when writing modulo equations. Formally, congruence is the same as equality, except that the left-hand and right-hand sides are equal modulo some number. So in equality, you know that the left-hand and the right-hand side are like inherently equal. With congruence, they're equal modulo some number. And thus, 21 would be congruent to 9, which is congruent to 1 modulo 4. You can see how 21 and 9 are both 1 more than a modulo 4. And then, again, 120 is congruent to negative 1, which is congruent to 10 modulo 11. So you can see how you can actually have negative integers in a modulo as well. And like the intuition for that is, think about like 120 being 1 less than a multiple of 11. You know, 11 squared is 121. So you have a negative 1 as the modulo, and then that's also the same as saying 10 modulo 11. Again, this should be reviewed. Modulo is very useful in mathematics, but especially so in computer science. It's used a lot in computers, but if you haven't seen it before, don't worry. Just probably want to get familiar with it in your own time as well. It's generally a useful skill to have. So we'll just review some of the properties of the modulo. So there's the addition rule. So if you have A is congruent to B modulo n, and C is congruent to D modulo n for some integers A, B, and N, and C and D as well, I guess, then A plus C and B plus D is also congruent to each other modulo n. And then, it's pretty straightforward. And then following from the addition rule, you can see that, again, if A is congruent to B modulo n and C is congruent to D modulo n, then A minus C is obviously congruent to B minus D modulo n. And then, that follows from the addition rule. If you prove that, then you also have the subtraction rule. Then the multiplication rule, if A is congruent to B modulo n and C is congruent to D modulo n, then AC is congruent to BD modulo n. That also follows from the addition rule. And then the division rule is a bit more tricky. So it says that if A is congruent to B modulo n, then A divided by K is congruent to B divided by K modulo n divided by the greatest common divisor of n and k. And then K must divide A and B for some integer K. So let's kind of break this down and pick apart what it means. So first off, K has to divide both A and B. And K divides A for some integer A means that K is a factor of A. So basically, A divided by K and B divided by K has to be an integer. You can't have decimals in the modulo. We won't go into what happens if you try and use like rational numbers in modulo because it gets complicated. So we'll just stick to integers for now. And then for integers, as long as K divides A and B, you can divide by it. But the key thing to note is that the thing you're doing modulo with also changes the number. It becomes n divided by the greatest common divisor of n and k. So basically, if your number k, which you're dividing by, shares a factor with n, the greatest common factor of both of them gets divided out of the modulo. And we won't be proving why these properties exist, but you can prove them as an exercise in your own time, and it's you can think about why that has to get divided out. And then following from the multiplication rule, you have exponentiation. So if a is congruent to b modulo n, then a to the k is congruent to b to the k modulo n. So yeah, you want to drill these properties down. Modulo is useful on some math contest problems as well, and also maybe like the CCC. So yeah, definitely get familiar with these rules. And then we have an example problem. So the problem is very simple. It's just asked what are the last 2 digits of 7 to the 1942. So the first thing to notice is that if we could somehow compute the residue of 7 to the 1942 modulo 100, we would get our answer. But it's not immediately obvious how we would do that, right? So if we try some small values of 7 to the k modulo 100, we find that, okay, when k equals 1, 7 to the k is just 7, so modulo 100, that's just 7. So the residue is 7. Then when k equals 2, we get a residue of 49. Then when k equals 3, again we get a residue of 43. But then when k equals 4, we find that we get a residue of 1. And this is very important because if you notice, then k equals 5 has a residue of 7, and it loops back to the start of our cycle. So whatever the k is, 7 to the k is just congruent to 7 to the k modulo 4, modulo 100. And yeah, therefore that makes the computation really easy actually. We just find whatever 1942 is modulo 4, plug that into k, and then we get our answer. So 7 to the 1942 is congruent to 7 squared, which is congruent to 49 modulo 100. And therefore the last 2 digits are 4 and 9. So yeah, the key things to note here are the modulo 100. You have to figure out that you have to compute this residue modulo 100, and then you have to try some small values and figure out that there's this cycle in the residues. So you can kind of see how number 3 problems kind of require practice. It's hard to build this intuition on the fly, like if you've never seen a problem like this before. But once you do, some of the different types, it becomes more straightforward. And then this next thing we'll talk about is the Euclidean algorithm. So this comes up in grade 12 CS, so pay special attention to this section. So the Euclidean algorithm is an algorithm for computing the greatest common divisor of 2 integers m and n. And without loss of generality, let's just say that m is greater than n. So first step in the algorithm is to divide m by n and then write it in like the extended division format. So m is equal to n times some quotient plus some remainder r naught. And then for each subsequent step, we move whatever we divided by, and then we make that our big number basically, and then we take the last remainder and then we divide our new number by itself. So then we get n is equal to r naught times some new quotient plus some new remainder. And then we do the same thing, and then we shift over the thing we divided by. We make it our new big number, and then we divide our new remainder by this by itself, right? So then r naught is equal to r1 times some quotient plus some new remainder. And then we keep doing this step until we get a remainder of 0. And when we encounter a remainder of 0, then we know that the last number we divided by is the GCD of m and n. So that's a little confusing explaining it. Let's try an example so we can see kind of how this works. So let's find the greatest common divisor of 4171 and 2231. So notice that 4171 is 2231 times 1 plus 1940, plus a remainder of 1940. And then this is the same thing as saying that 2231 fits into 4171 once with a remainder of 1940. And then now we drag this 2231 over to the left and the 1940 here, and then we divide this into the 2231. So we get that 1940 fits into 2231 once plus 291 plus a remainder of 291, right? And then again we repeat, 291 fits into 1940 6 times plus a remainder of 194. 194 fits into 291 once plus a remainder of 97. And then 97 fits into 194 twice plus a remainder of 0. And that was our exit condition. So therefore 97, which was the last thing we divided by, is the GCD of the two numbers. Yeah, you can review these slides if you kind of want to build an intuition or maybe try some examples on your own to really solidify the concepts. And then if you want a challenge, you can try writing an implementation in Python, or even better, processing if you know it. Maybe try writing like a method to compute the GCD of two numbers A and B and then return the result. And then that will prepare you for, I think, like the first unit of grade 12 CS. I guess I'll take any questions before we move on to, whoops. Okay, so how is -1 modulo 10 equal to 11? Hold on, let's go back. So this is -1 modulo 11 is congruent to 10, right? So it would be -1 modulo 11 is equal to 10. Yeah, it's a little bit weird when you start writing it on multiple lines. You technically don't have to write the bracket modulo 11 on each line. You can just keep it for the end. Sometimes some people don't even write it. They'll write it like once at the top of the proof, and they'll just like not write it at the rest, and it gets even more confusing. But yeah, if you have any other questions, whoops, kind of spoiler there. Ask them now before we move on to the Toshin function. Nothing? Okay. So next up, we'll cover some of the, there's two functions that are important to cryptography that Trevor will bring up when he starts talking about the encryption algorithms. So the first one is called Euler's Toshin function. So Euler's Toshin function of a positive integer n is defined as the number of positive integers less than or equal to n that are relatively prime to n. So two positive integers are considered relatively prime if they do not share any common factors. So like 7 and 8 are relatively prime because 7 doesn't share any common factors with 8. And so Euler's Toshin function of some positive integer n is written as 5n, and yeah, it's read as 5n. And if you want to read more about it, Art of Problem Solving, otherwise known as AOPS, has a good article on it. So for example, notice that 8 is equal to 4, since 8 is relatively prime with 1, 3, 5, and 7. And then it's not relatively prime with like 2, 4, 6, and itself. So therefore, yep, there's 4 numbers that it's relatively prime with, and that are smaller than itself, and therefore 5, 8 is 4. And then a thing to notice is that 5, any prime number p, is just 1 less than that prime, since any prime is relatively prime with everything less than or equal to itself. Yeah, to p besides itself, right? P, like a number cannot be relatively prime with itself since it shares itself as a common factor. So it's just p minus 1. So that's something that will be useful when Trevor starts talking about RSA. And then another interesting formula is that given some number n and its prime factorization, so I assume you guys know what a prime factorization is. So in this case, n equals p1 some prime, p2 some prime, p3 some prime, all raised to respective exponents. So I think like I should have probably provided an example, but for example, let's say n equals 10, then it's equal to 2 to the 1 times 5 to the 1, where 2 and 5 are prime. And so this can be done for any number in general, but I think that's already in the curriculum in like grade 8, so you should already be familiar with that. And then phi of n is then just n times 1 minus 1 over the first prime times 1 minus 1 over the second prime, dot dot dot, for all the primes in the factorization. So that's a cool formula. Again, we won't prove it, but I guess it can be useful in some more advanced math problems or math contests. Yeah, don't stress too hard if you're not familiar with, or like if it doesn't make a lot of intuitive sense, but you'll definitely run into it if you start studying like number theory in like university or maybe some like really complicated math problems on like Olympiads. Are there any questions about that? Nope. Okay. And then the next function we'll talk about is the Carmichael function. So Trevor's also going to be mentioning this one. The Carmichael function lambda of n is defined to be the smallest positive integer, such that a to this Carmichael function of n is congruent to 1 modulo n for all positive integers a smaller than or equal to n, which are relatively prime to n. So again, AOPS has a good article on it. Given again some prime factorization of n, this Carmichael function lambda of n can also be stated as the lowest common multiple of the Carmichael function of all of like the prime factors raised to their respective exponents. So it kind of has this interesting recursive formula based on the prime factorization of the number you're trying to compute the Carmichael function on. And then again, the Carmichael function has this property where if you do lambda of some prime p, it's the same as phi of p, which is p minus 1 for any prime p. And the Carmichael function is, it's important in cryptography as it's used in the RSA algorithm, which we'll see shortly in Trevor's side of the presentation. So are there any questions with any of the number theory stuff I've talked about so far, or any of these special number theory functions? You can unmute or you can type in the chat if there's anything.
So I'm going to be talking about a couple of applications of number theory, which is cryptography. It's pretty cool. Okay, I think almost everyone's in. Let's get going. So first, let's talk about what is cryptography. So Wikipedia says, cryptography is secure communication in the presence of third parties. So sometimes we want to communicate information only to specific people. And in the presence of third parties means that we want to make it so that eavesdroppers don't understand what we're saying. So I'm going to go through a couple of terms or buzzwords. In cryptography, a code is just an encrypted message, and sometimes it's also called ciphertext. Ciphertext. Yep. Encryption means to turn meaningful information into gibberish, while decryption means to turn gibberish back into meaningful information. And we use a secret method to encode and decode messages. Without knowing the decoding method, a code is about good as gibberish. So that's how we communicate securely. So you guys might be wondering, so what? Why do we care about encryption? Well, the thing about the internet and communication between computers is that people can eavesdrop on what we're saying. They can intercept information that's in transit. So if you're buying stuff on Amazon and your credit card's being passed around, the information had better be encrypted, or else your credit card might end up something like this. I'll start off with a simple cipher or a simple encryption technique called the Caesar cipher, which you guys might have heard before. Basically, the method is you shift every letter in the alphabet some amount to the left or right. So for example, a left shift of 3 would turn the alphabet A, B, C all the way to X, Y, Z to D, E, F all the way to A, B, C. And that's illustrated in the image in the bottom right. So letters correspond with another letter in the same position. And then for every letter in a message you want to send, you substitute it with the corresponding letter in the shifted alphabet. So for example, the message A help turns into, well, A corresponds with D, as you can see here in this thing. And then with the rest, we get D, Kahos. And this is our code. And then what a key is that we use a key to encrypt or decrypt messages. In this case, our left shift of 3 or our like alphabet that we shifted to the left 3 times. So D, E, F to A, B, C, that's our key. And we can use that to decrypt and encrypt messages. So when I send another person D, Kahos, then they can use the key and get A help. So both communicating parties need a key to understand each other. The problem with this kind of it's called a substitution cipher, where you substitute every letter in a message with another letter. So the problem with a substitution cipher, like the Caesar cipher, is that both parties need to have the same key. Like both ends of the communication, like both people need to know that the alphabet has been shifted left 3 times. And this technique is called symmetric key encryption. And the problem is, how do we actually send the key to the other party? Well, option A is to meet up at the park next Saturday at 3 p.m. And option B is to send the key to them over an unencrypted connection. Well, the problem with option A is that we might be lazy and we don't want to meet up at the park. Or sometimes it's actually just impossible to meet up with a person if you guys are on like the opposite sides of the earth. And the problem with option B is that eavesdroppers can just get the key while it's in transit and then use it to decrypt our messages. So the solution for this is called, well, we're going to go through something called Diffie-Hellman key exchange. And it uses number theory. The most important principle here is that a to the x mod b to the y mod b is equal to a to the xy mod b. Or you could use a congruent sign and remove this mod b here. But I use equal signs. Okay, so let's go through what you do in Diffie-Hellman key exchange. So let's say there are 2 people, Alice and Bob, and they want to send messages between each other, or they want to have a shared key. Well, first thing they do is they agree on 2 numbers, P and G, and publish it to the public. So what P stands for is P stands for prime. It's supposed to be some large prime number. And G stands for generator, which is some other number. The first thing that Alice and Bob do is they make their private key. Alice makes the private key X, and Bob makes the private key Y. And they're just some integer. Then they do this operation to get a public key, which is they take G to the exponent their private key. So in Alice's case, that would be G to the X, and then take it to the mod P. And then in Bob's case, his public key is equal to G to the Y mod P. And then they trade their public key over an unsecured connection. And then Harold is able to see the public keys, but we don't actually use the public keys in encryption. What Alice and Bob do now is for Alice, she takes Bob's public key and takes it to the exponent of her private key, and then takes it to the mod P. And that gives us S, which is our shared key. And then Bob does the same thing, except with his private key. He takes Alice's public key, takes it to the exponent Y, and takes the mod P. And that's also equal to S. These 2 numbers are actually the same. So why are the shared keys the same? B to the X mod P and A to the Y mod P. Let's go through it step by step. So we know that B is equal to Bob's public key, which is equal to G to the Y mod P. Well, B to the X mod P is just equal to G to the Y mod P to the exponent X mod P. And then from that rule that I put in really big text earlier, we know that G to the XY mod P is equal to G to the Y mod P to the exponent X mod P. So that's our shared key. And we can use the same logic for Bob, where he takes A, which is Alice's public key, and that's equal to G to the X mod P, and then he takes A to the Y mod P, which is equal to G to the X mod P to the exponent Y mod P. And that's also equal to G to the XY mod P. So what might look familiar here in this identity, I'll go back to this one here, is that it looks like one of our exponent laws, right? Where it's A to the X to the exponent Y is equal to the product of the exponents. So why do we use the mod function, the modulo function? Let's go back. Well, if we just use an exponentiation function like g to the x, g of x is equal to a to the x, Well, this function increases systematically, meaning that we can get x easily just by taking a logarithm, right? If we did this, which is f of x is equal to a to the x mod b, this is called a modular exponentiation. When x increases, f of x gets scrambled between 0 and b minus 1. Because you can imagine taking the mod as like going around a clock, where it loops around at the end when a to the x reaches b. And this scrambling is really good for cryptography because solving for x in this case is really difficult to do. The best method currently is to just try every number. And when you end up using really, really big numbers, it gets really, really difficult to actually find x because you have to try every number, right? And this is called the discrete logarithm problem. And because this problem is so hard to solve, that's why this function works. In people call it a one-way function because with the output of this function, you can't get the input. And that's why we use it for cryptography. Okay. Now let's talk about RSA. RSA stands for Rivis Shamir Adelman Crypto System. Well, not the crypto system. No one really remembers the names, we just call it RSA. This, as opposed to like the Caesar cipher, is an asymmetric key system. So, like the Diffie-Hellman key exchange thing, there's public and private keys. Except instead of having the same private keys on both sides, you have one person has a private key and the other person has a public key. So, as an example, what Bob would do is he would create a key pair and publish the public key. And then if Alice wants to tell something to Bob, she would use the public key to encrypt her message. And then Bob can use the private key to decrypt Alice's message. Harold would have access to the public key, but since the public key is only good for encryption, then he can't use it to actually decrypt the message. So the public key is like a lock on a message, while the private key is like the key to that lock. So let's go through an example. Alice wants to send a message to Bob. She wants to send, let's just say, the letter C. So we have Alice and Bob in the public space. First thing Bob does is he publishes a private key and a public key. And in this case, we're going to say the private key is the two numbers 11 and 14, and the public key is 5 and 14. And these numbers, they have a very specific relationship with each other, and we'll see how to actually generate key pairs in the next slide. So first thing is Alice takes C, and let's just say that C is equal to 3, because C is the third letter of the alphabet. And then what you do is you take the 5 in the public key, or the first letter, the first number, take it to the exponent 3, and then take it to the mod 14, which is equal to 1, or A. And then Alice would send A to Bob, and Harold can see the letter A, but he doesn't know the original message. And he also has the public key, but you can't use the public key to decrypt the message. Bob then uses his private key to decrypt the message, which he takes the 11 here, takes it to the exponent 1 for the A, and then takes the mod 14, which gives us 3, and that spits out C. To actually generate a key pair, you have to do something very specific that makes it hard to find 1114 from 514, for example. So let's just call the public key the two numbers E and M, and the private key the two numbers D and M. And M is just like the modulo. This is what we take the modulo of. The first thing you do is you choose two distinct prime numbers, P and Q. And M, the thing that we use for the modulo, is just equal to P multiplied by Q. And then you choose E to be some integer such that 1 is less than E is less than the Carmichaels of M. And E and lambda M are coprime. So they have no common factors, except for one. And then you choose D such that D multiplied by E modulo the Carmichael's M is equal to 1. And what this little expression is saying is that it's saying that D and E are modular inverses. And only numbers coprime to lambda m have a modular inverse in this case. And we can solve for modular inverses, so we can solve for D using the extended Euclidean algorithm. But that's beyond the scope of the lesson for now. All right. So does anyone have any questions about encryption and cryptography? Let's check the Discord.
Oh, can you hear me?
Hello. Yep.
Was any of the encryption methods has anything to do with the German Enigma machine, or is it completely some other sort of encryption?
The Enigma machine is a type of encryption. If I remember, I think it was a bunch of substitutions, and it's really funny. But yeah, oh man, I researched it before, but then I forgot about it. Yeah, but the Enigma machine is definitely related, and if you're interested, you can definitely research more about it.
Okay.
Victor asks, how does Shor's algorithm defeat RSA? And if Cristian has an answer, he can go ahead. Yep. So the problem that makes it hard to find like the private key in RSA is that you have to factor a really, really big number. And factoring is hard to do with computers. If we just go back a couple slides, see that the modulo is equal to PQ. So I'm pretty sure what people need to do to crack RSA is that you need to actually find P and Q from M. And to do that, you need to factor it, which is difficult. Okay. Anything else? Questions? Concerns? We can move on to hashing, which is actually really useful. Okay, let's move on. So what is hashing? You guys might have heard that word thrown around a bit. Basically, a hash function maps data of arbitrary size to some sort of value. So in this image here, you can say like John Smith becomes 2. And in general, hashing is used to convert data into some numerical representation. And ideally, that representation is unique. The definition of a hash is that it's the value returned by the input of a hash function. So the hash of John Smith is equal to 2. And other names are hash values, hash codes, and digests. And hash functions are most commonly used in hash tables, and you might see those a lot in CCC and stuff. So I'm going to go through a couple of properties of a good hash function. Yeah, we'll get back to that. So one, a hash value is fully determined by the input. That means it's deterministic. So it's not like random, or every time you put in the same input, it changes. Ideally, the entire input is considered. So like if you had John Smith, it wouldn't just look at the first and last letters. It would look at every letter. The distribution of hashes should be uniform, meaning that for there should be an equal chance for every possible hash to occur given random inputs. So it shouldn't be like when you put in a bunch of random numbers, the hash function usually generates numbers that are around like 5. It should be the distribution should be uniform. So like it's random. Yep. My explanation was kind of bad. But if you guys have any questions, I'll be happy to clarify. Okay. The next is that a small change in the input should cause a big change in the output. And that's illustrated here. So this is called the avalanche effect. And basically, yeah, a small change in the input causes a big change in the output. For example, in this specific hash function, the input 000 generates this mess, and the input 001 generates this other mess. But if you notice, these two are actually really different, given how similar 000 and 001 are. And another property of a good hash function is that there should be a low probability of collisions. So what a collision is we saw one on the last slide, which is if two inputs generate the same output. So for this hash function, John Smith and Sandra D, they generate the same output or the same hash. And that's usually pretty bad. But I'm pretty sure sometimes collisions are unavoidable for hash functions. So yep, a collision is just different inputs generating the same output. A cryptographic hash is a type of hash function that people often use in cryptography. And there are some specific conditions that need to be fulfilled for a hash function to be cryptographic. So a hash function h of x is considered to be a cryptographic hash if it satisfies 3 properties. One is pre-image resistance, which is given h of x, or the output of the hash, is hard to find x. So ideally, the hash function is one way. The second condition is second pre-image resistance, which is given an input x1, it's hard to find another input x2 such that the output of the hash functions on those two inputs are the same. And the reason why it's called a preimage resistance is because the preimage attack is a type of attack on a hash that does this, that like inverts the one-way function or does this thing. And the third property of a hash function or a cryptographic hash is collision resistance, which is it's hard to find two distinct inputs that yield the same hash. And all three of these together give you a good cryptographic hash that people use in cryptography. So let's go through an example of a, well, in air quotes, bad hash function. And it's called identity hashing. So our identity hash, so this function, identity hash of x is equal to x, which means to just do nothing. And the problems with this one is, well, inputs near each other produce similar hashes because identity hash of 1 is equal to 1 and identity hash of 2 is equal to 2. Ideally, hash functions should have the avalanche effect, right? The second problem with the identity hash is that it's not one way, because since we do nothing to the input, with the output we can sort of find the input, right? Like with 1, it's obvious that the input is 1. And the third problem is that this hash function doesn't compress the input into a more compact representation. So sometimes hash functions are used to like sort of give unique identifiers for things that would be too large to store, too large to store, right? So this just doesn't do any compression. If you had identity hash of 1 trillion, the output would be 1 trillion. But identity hashes are pretty awesome if the range of inputs are small and evenly distributed. And the thing is, there's actually no such thing as a bad, like a really, really bad hash function that you would never use unless it just doesn't work. So it's like a case by case basis where it's for some situations, different hash functions are the best. And yeah, this one, identity hashing is not very good for cryptography because it's obvious from the output what the input is. So here's an example of a better, well, in air quotes, better hash function, which is called modular hashing. So mod hash of x is equal to g to the x mod p for two numbers p and g. And that might look familiar from Diffie-Hellman key exchange. P should be a prime number that is larger than the upper bound of x, and g is just some random number. Well, ideally, g would be something called a primitive root of p, but we won't be talking about those for now. So we know from Diffie-Hellman's key exchange that modular exponentiation is a one-way function, which is awesome. And inputs are compressed between the range 0 and p minus 1 because of the modulo. Unfortunately, though, the only condition of the cryptographic hash that mod hash really satisfies is that it's one way. So it's still not a very good cryptographic hash function. Some commonly used actual cryptographic hash functions are, the first one's MD5, which is called Message Digest 5. And the next one's called SHA-1, or Secure Hash Algorithm 1, and this one's outdated. It's got replaced by SHA-2 and SHA-3. And you guys might have seen them before when you've maybe installed some software, and they're like, "Oh, do you want to perform a SHA-2 checksum check?" Yep. And these are all hash functions. And they're way better than mod hash and identity hash for cryptographic purposes. But they're also way more complicated, which is why we're not going into detail about them. Okay. So the first application of hashing are hash tables. And they're the most common use for hash functions. In Python, dictionaries are implement hash tables. So if you hear Python dictionary, it just means a hash table except in Python. And hash tables, what they do is they convert the keys into indices for an array using a hash function. So if you had the key, like carrots, the hash function would convert it into an integer index. And then with that index, it would store the key's value into an array. So the access, insert, and delete complexities of a hash table is O of 1 best case, which is why they're so awesome. I use them all the time. And their worst case is O of n, actually. And this is caused when there are lots and lots of collisions, when a table is almost filled. And when there's a collision in a hash table, what they usually do is that they just look for the next available space to place a key value pair. Okay. The next thing I'll talk about is checksums, which I mentioned a bit earlier. So the reason why checksums exist is because data can get corrupted when they're being communicated over the internet. So checksums are used to verify the integrity of files and data sent between computers. So checksums are just computed when you find the hash of an entire file. Because in the end, files are just still stored as a string of bits, right? So you can still find the hash of those. And what happens is that files are pre-computed and sent, hashes are pre-computed and sent along with the files. And then the receiver can recompute the checksum from the received files and then compare with the pre-computed checksum. And there's any difference, then you know that something in the file has been corrupted. And due to the avalanche effect, small differences, a small corruption will usually really, really change the digest. So for example here, if someone wanted to send the red fox jumps over the blue dog, they would first pass it through a checksum function and then get this number and then send this checksum and the message to the receiver. And then somehow in transit, this message gets corrupted, and the V in over becomes a U. And then when that gets passed through the checksum function on the receiver's end, we get a way different hash than the pre-computed checksum. And when they're different, we know that something's changed, and we need to resend the files. And like I said before, MD5 and SHA are commonly used for checksums. Okay. The last application of hashing that I'll be talking about are password hashing. So, how does Facebook store everyone's password? The wrong answer is in a giant passwords.txt file with everyone's passwords. Because if there's some sort of data breach and someone gets a hold of passwords.txt with everyone's passwords, then we'd all be screwed. So generally, cryptographic hashes of passwords are stored in passwords.txt. So when a person signs up and sets their password, then you would find the hash of their password and put it onto passwords.txt. And because cryptographic hash functions are deterministic, which means that every single time for some input, for the same input, it will give the same output, and ideally that they're collision proof, then we can just pass a user's password input from the login through the hash function and check if it matches with the digest in passwords.txt. And then because cryptographic hashes are one way, HackerMan won't be able to get your passwords from the hash gibberish in passwords.txt. And this is how companies usually store everyone's passwords, by using cryptographic hashes. And I'm pretty sure that's all we really had to talk about today about number theory and its applications. Obviously, we didn't really go too much in depth into the really the industry use ones, like MD5 and SHA. So yeah. Sorry, my mom just came into my room. It was like, "Hi." Okay. Yep. That's all I really had to talk about for applications number 3. If anyone has any questions, feel free to ask them in a challenge room.